Hello there and welcome back to this video series on control systems. Over the past few videos we have been looking at transient response and steady state response of first order and second order systems, and in specific in the past video we have seen response of second order overdamped system subjected to a unit step input, and we have also seen that it is possible to approximate that response by truncating some terms. We will try to continue that discussion in this video, and we'll try to specify the transient response specifications of an underdamped second order system when it is subjected to unit step input. We can see that we can characterize it with four constants, four values, and we'll see what are those values and try to derive those. It would be very beneficial if you go through the videos on Laplace transform, that is 7 to 11 in this series, and also 31 to 36. It wouldn't hurt to go over Laplace transforms more than once. The more you do, the better it would be. And carefully take notes while you watch these videos 7 to 11 or 31 to 36. Keep the notes handy and also solve all the problems mentioned in these videos. There are four terms associated with description of transient response of second order underdamped system, and those are rise time indicated by P subscript R, peak time T subscript P, peak overshoot M subscript P. Very many times we specify percentage peak overshoot, that is overshoot divided by steady state value multiplied by 100, that we call percentage peak overshoot. Then settling time T subscript S. This settling time, we define two settling times. One is a 2% tolerance band settling time. Second is a 5% tolerance band settling time. We call them as 2% settling time and 5% settling time. These quantities are described with respect to the plot shown in the next slide, and we derive these for a second order underdamped system. The plot here shows the response of a second order underdamped system when it is subjected to a unit step input. You can see that the output rises, reaches a peak, and then kind of comes down and then goes up and so on. It's kind of oscillatory about a steady state value at 1. And that value of 1 is also constant input 1, that is step input 1. Now these terms you can see, when you give a step input, the response rises, and for the first time comes to the steady state value. The time at which this happens is called rise time T sub R. Similarly, it continues to rise and attains a maximum value that we call the peak time. The difference between the steady state value and the maximum value, that is this y-intercept, segment AB, is called overshoot. And then in the process it comes to a time T sub S, where the response always lies within a tight tolerance band around the steady state value. That is, when once it comes to this 2% settling time, it will always remain in between these two lines. These two lines are 0.98, that is 2% less than the steady state value, 1.02, that is 2% more than the steady state value. So when once the response comes to this point D, at which the settling time Ts, settling time is Ts, then from point D onwards, the subsequent portions of the response always lie in between these two lines. Rise time is the time required for the response to rise from 0 to 100% of the steady state value when subjected to unit step input. If it's an underdamped second order system, the steady state value is whatever is the magnitude of the input given, that is 1 unit, and rising from 0 to 1, the time required for the response to rise from 0 to 1 is the rise time. In some textbooks they may mention from 10 to 19%, maybe for critically damped or over damped systems, but for underdamped system, this is what will follow. Rise time is the time required for the response to rise from 0% to 100% of the steady state value. Thus we say that at time t is equal to tr, response C of t is 1, which is the steady state value. We know that the response is so and so expression. This is what we derived in one of the previous videos, and we want this response to be 1. So you have this term multiplied by sine is equal to 0. This cannot be 0. This gets very small, but theoretically this term e power minus epsilon omega n by square root 1 minus epsilon square, this term theoretically never is 0. So the only possibility is this term has to be 0, because this 1 and 1 get cancelled. So if this whole has to be 0, this sign has to be 0. This sign is 0 at several instances, 0, pi, 2 pi and so on. 0 is a trivial solution, so the next non-trivial is pi. So we say omega d tr plus phi is equal to pi. That is, we have tr is pi minus phi divided by omega d. Recall that phi is defined by square root of 1 minus y square by xi. Omega d is omega n square root 1 minus epsilon square. Peak time is the time at which the response to unit step input attains maximum value. Maximum value occurs when the derivative is equal to 0. So at t is equal to Tp, the derivative is 0. So you differentiate the expression, equate it to 0, rearrange the terms and do a little bit of simplification. The simplification is sin A plus B. A is omega d Tb, B is phi. That is sin omega d Tp cos phi plus cos omega d Tp into sin phi. That is, this is the value of sin expanded. Similarly, expand cos and simplify. You see that this Tp comes out to be pi over omega d. We define peak overshoot to be Ct minus 1 magnitude. Okay, this maximum occurs at time t is equal to Tp, because we evaluated the derivative equal to 0 at Tp. Okay, so this, if you simplify, we know this is this and Ct is this. Ct minus 1 is magnitude of this term, and this magnitude evaluated at Tp, that is pi over phi, I think, pi over omega d. Pi over omega d, if you substitute in this expression, you get peak overshoot to be e power minus pi xi over square root 1 minus xi square, and expressed as a percentage multiplied by 100, that will give you percentage. Note carefully that the peak overshoot is defined only with xi. It does not depend upon omega n. So in some sense you can say that the relative stability is determined by the damping ratio. The last term is the settling time. I'll define what is 2% settling time, and you can substitute 5 in its place to get 5% settling time. 2% settling time is the duration after which the response always lies within 2% of the tolerance band. Okay. okay, around the steady state value. Similarly, 5% can also be defined. So this gives the condition for 2% settling time. This gives the condition for 5% settling time. Okay. I leave it for you to derive. 2% settling time is approximately 4 over xi omega n. 5% settling time is 3 over this epsilon omega n. To summarize, we say that these 4 numbers describe the response of second order under damped system, and these 4 terms are rise time T sub r, peak time T sub t, peak overshoot MP or percentage peak overshoot, settling times. Okay. Carefully note that this MP depends only on the damping ratio epsilon, whereas all the other 3 depend both on omega n and damping ratio, natural frequency and damping ratio. That's all we have for now. Have a great day.